In this video, we will show how to apply a centrifugal load and to use local refinements in order to set contact conditions and solve for a contact force or contact point. So here we have the piece of the clutch. We've trimmed away some of the extra areas, so we can just look at this area. And you also notice that we've broken up this face into several smaller pieces. Similarly, on the other side, we've broken that up, and likewise we've broken this piece. So that allows some easier refinement. So we'll go ahead and talk, let's just start at the top and work down. So connection. So contacts is a way of modeling interactions that can come and go. And so let's go ahead and create a contact, and we're going to make a frictional contact, and we will have, we'll start with our surface that's moving, and I'm going to select that face into this place, its surface it's going to target. So I think of the target as the stationary interface. Now I can set a coefficient of friction. Let's go ahead and leave that at 0 right now for this purpose. Okay, there are a number of other things about how it's going to detect the method, how much it's going to penetrate. So what it's looking for is a point at which a node here goes through the surface on the other mesh. And when it does, it's going to calculate, based on the stiffness of that surface, it's going to push back with a force back against that element, and until it tries to reach an equilibrium at which there's negligible penetration. But this is a nonlinear problem to solve, and it is can be challenging. So let's look at our mesh. We need to get some fine refinements in here in particular regions. So let's go ahead and first let's put our method. And I'm going to select our geometry, select both of them and apply, and I'm going to suggest a multi-zone mode. Try to get some brick elements. This is planar, so and relatively thin, so that shouldn't be too challenging for it. Let's create our sizing. So one of the options is for the contact sizing. The nice thing is I can just come down here and select my contact pair, and I can set an element size, and let's see, we're in meters. So the finer the elements, the easier it's going to be to detect that penetration and resolve it. If they're too large on the contact face, that could be a challenge. So we want that to be small. We also, let's just go ahead and set a sizing constraint, and let's select the face. So these faces right here are important because that's the area that's actually bending. And in this region, where mostly it's a mass creating a force, and so it doesn't take a lot of refinement in there, but in this region it's a stiffness question, so we want to make sure we have a fine enough mesh to handle that. And we'll just go ahead and create 1 millimeter elements there and see what that looks like. Let's go ahead and create our mesh. So meshing is complete. We'll select show mesh. We can see we're getting some fine elements along the interface there, finer there. We have several elements through the thickness. It's really looks very nice from that perspective. I'm happy with the contact mesh. I think I'm just going to make this region a little bit smaller. So this mesh is adequate, but to look at how it might be refined, you run into a few issues with the multi-zone setting. Particularly, you can't use the refinement on those faces on the two sides, and so we could look at some other options, which would be to go perhaps to a hex dominant mesh. But it is a good opportunity to compare different options. I'm going to go with the hex dominant, so it allows it to use some local element refinement, local non-hex elements, and let's see what that does for the mesh. Okay. So this is using predominantly tetrahedrons, it appears, and you know it kind of does what we need to. We have more refinement than we need to along here. I think we could adjust that by changing our inflation options. Let's move this back to 1.2. And this is all right, but I'm going to just increase the level of refinement there by 1 notch, and we can resolve that to see how it does. Actually, rather than solve, it would be better to just update the mesh since I haven't set my boundary conditions yet. It's not going to be able to solve the model well anyway. Okay, so you see a little bit finer mesh here in the bending section. We have still a fairly fine mesh out here at the tip, more than I need, but I'm going to try running that and see how well that works. But we need to, before we do that, we need to specify our boundary conditions. So in this case, we can apply the surface down here is not going to move in our frame of reference. So I can put a fixed support down there. Any stresses from constraints in the transverse direction should be minimal. They certainly won't affect the calculated deflection of the tip, even if we get a little bit of stress down here from that. Now I need to apply my loads, which in this case we're going to simulate a centrifugal load. So that's going to be an inertial element added to each piece based on its position. And so let's create, let's see, there we go, inertial loads. And we can do a rotational velocity. And so let's select our body. We'll just apply it to the inner body, the clutch. Apply that one. I could apply it to the outside. It doesn't make a lot of difference, but this will be preferred. Now let's go ahead and pick our components. We want to spin that around the z-axis, and let's go ahead and put in 100 radians per second. That'd be roughly 1,000 RPM to start with. It tells us our direction, which would put this in an aggressive loading. I'm going to actually change that to a negative 100. And we need a rotational point. And we want to go ahead and have it rotate around 0, 0, 0. In doing this initial analysis, I goofed on this rotational velocity. You notice it's rotating around a coordinate 0, 0, 0. Which are not actually the center of this object. So I can change that. Let's go ahead and create a new one. Rotational velocity, and we'll go ahead and create the values. And then the key thing is the axis. And I can pick, if I pick a cylindrical surface, so make sure if you had a face select. So I have a cylindrical surface there, and apply. Notice it's going to put that right at the center, so that I would have a correct rotational velocity. So that's something to make sure you do in your analysis, though the rest of what you see is made with the wrong rotational velocity. So that may affect some of the results that you see in those plots. It may make them look different than what you get. Location. Okay, and then we also need to support the outer housing. So let's do another fix support, and just to make that really easy, we'll select that outer surface there. Since we thinned that down, that'll help compensate for the fact that we thinned it down. Now I can put in, one thing that may be helpful is to define a coordinate system. Let's see, so we're going to insert a coordinate system, and rather than Cartesian, we're going to select cylindrical coordinate system. And make sure we've got this defined properly. Let's select this surface there. And that has gone ahead and put that at the center. And so now I can see that X is radial, Y is circumferential, and Z is the out of plane deflection. Now, with our solution, we can plot our directional deformation, and we can select about the x-axis, so that would be radial deformation. It can help us see where it's largest. So let's just go ahead and we'll go ahead and plot total, and let's look at the equivalent stresses too, so we can see what's happening. And now we've defined our contacts. We have our mesh. We've set our boundary conditions. Click on that, we can see what those are. So we have fixed support, and a rotational velocity. And we have the contact interface that matches. And mesh looks adequate, so we can go ahead and solve this analysis. Okay. So this solved successfully. And you can see I have a warning though. And this is good to note. So this warning is good to be aware of. You notice that it is telling you that there's an issue with how many elements there are through the thickness. You can see that several places there's only one element through the thickness, which reduces the accuracy of the model. And so that is an issue with some aspects of accuracy. I don't think it will affect us here, but that's something that you would be wise to check and compare the impact of your solutions. Let's look at the solutions. So we look at our directional information. We see that the maximum radial deflection is occurring at this tip there. Right. And maximum total deformation is over here. Equivalent stresses. This is on the order of 27 megapascals. So for a polymer, that would be significant. In fairly localized regions, you can see that this is a bending load there. The peaks at the inside and outside. But the clutch is not impacted yet. In this case, it looks like the clutch is very close to touching, but we notice it's an auto scale that's larger than normal, so it is making it look closer than it actually is. Need to rerun this with much higher velocities. You can see here that I now succeed in deflecting far enough to engage, but I'm clearly penetrating through where I'm supposed to have a contact. And so there are a couple of things that might be at issue here. One of them is it's time to apply my large deflections. And that alone may be an issue. let's just also double check my contacts. Those look good. I mean, it may be that I should be having contact across the middle here instead of the tip, but I don't understand why I didn't catch that. So let's rerun that with just the change in large deflections. So you can see here that that made all the difference. Going to large deflections, now it is not penetrating through the structure. There is the question of whether where the contact is happening, and there are some tools to help understand that. And let's see. So we have a contact tool here that's going to insert the status, and we can also add a pressure. It may be interesting to plot the gap between those. So let's go ahead and evaluate those results. So we create those plots. So again, there's pressure goes up quite a bit. So there we can see where the peak pressure is. So it's kind of towards the middle of our contact zone. So that's encouraging. That means we've got it in the right region. We can also conversely look at the gap. So it goes from 0. That's a negative gap. Well, that's interesting. Not sure of the signs on that. Let's try looking at a different point in time. So this these are all negative. Let's look conversely at the pressure at that point in time. Retrieve that result. Okay, so it appears that there's no contact at point 2. So the negative gap would appear to be a space. So let's look at load step 3. Retrieve that, and we're seeing the first bit of contact there. And you can see in this case the pressures have gotten quite high by the time we got to step 4. It's about 54 megapascals. Let's look at our stresses. And this is clearly an unreasonable amount of stress. So it would require a redesign for the at roughly almost 3 gigapascals there in really some regions of this. Okay, so you kind of see we're looking at that now. Your challenge is to look and say, well, what is the maximum position here, the maximum load at which it begins to interfere and to touch. And so you could imagine that this contact status might be a good value. You could use any of these values, possibly some amount of iteration to find about where that point is. Right? And you will notice that let's see, retrieve that result. It's the same result we had before. And it will save some values at the in-between points generally, so that you can so there's some change. So it'll automatically interpolate as it does the nonlinear solution. So you can select these in order to help come approximate that value there. So we're getting pretty close to. It certainly dropped off the pressure quite a bit, and you could kind of continue moving that along to see where that limit is, and then maybe rerun something a little bit between those speeds. Right, so hopefully it gives you a little bit of an orientation about how to approach this, as well as some things, a little additional experience with the mesh, and we'll